Hello, everyone. My name is Liyu, and I work with Dr. Richard Liang at Florida State University. It is such an honor for me to participate as one of the finalists at SAMPE University Research Symposium. And today, I would like to present my research project on the mechanical and electrical properties improvement of the double-watt CNT composites from continuous water-assisted floating catalyst synthesis. I know that for a lot of you, this is probably the first time you have ever met me. So I would like to take just a minute to share my background. I got my Bachelor of Science in Polymer Materials and Science at Beijing University of Chemical Technology in China, where I received extensive education covering applied mathematics, polymer science, biomechanical, and chemical engineering. In 2015, I started my PhD journey in the interdisciplinary program of material science and engineering at Florida State University, and I have been happy ever after. Here is an incomplete list of the publications that I made during the past few years, including the journal and the conference papers. Okay, back to the project. When talking about improving the mechanical and electrical performance of CNT composites, a lot of work has focused on introducing bundle alignment or interface engineering. In this work, we try to trace all the way back to the beginning of the problem, which is the CNT synthesis. In our process, we introduce water as a cleaning agent to remove impurities and increase the catalyst efficiency. With that, we were able to continuously synthesize and collect double-watt CNTs with improved quality. In this talk, we'll talk about the improved CNT quality from different aspects and also the overall composite performance. Since the discovery of CNTs in 1991, various synthesized processes were tried or used, hoping to yield high-quality CNTs at a mass production level. Among them, the three mainstream routes are arc discharge, laser ablation, and CVD process. The first two methods, arc discharge and the laser ablation, rely on the carbon sublimation or vaporization under high temperature. When I'm saying high temperature, normally it's either 2,000 or 3,000 Celsius, which is the reason why they were proven to be impractical due to the high energy consumption and inefficiency. The conventional CVD process, on the other hand, requires remarkably lower synthesized temperatures for the CNTs to grow on a pre-deposited substrate. In earlier 2000s, a Japanese group took an innovative approach to introduce controlled amount of water vapor into the CVD process in synthesizing CNT, yielding single-watt CNTs as shown in this TEM image with over 99.8% purity. They believed that the water vapor served as a weak oxidizer and selectively removed the amorphous carbon without actually damaging the CNT network. With a prolonged catalyst lifetime, this technique is anticipated to provide a simplified approach for achieving high purity CNT synthesis more efficiently. While the conventional substrate-based CVD tune the nanotube diameters by precisely control the catalyst sizes, the significant batch-to-batch variations remain a big drawback. On the other hand, with a continuous catalyst feed and controlled synthesized conditions, the floating catalyst chemical vapor deposition process is more suitable for mass production, and it could achieve flexibility in product forms, such as yarns or sheaths, depending on how would you like to collect. Although still somewhat controversial, one of the most widely accepted mechanisms for FC-CVD process begins with the iron-containing precursor, ferrocene, decomposing at high temperatures to release the iron atoms located in the middle, and they form nanoparticles of different sizes after interparticle collisions and agglomerations. Similarly, the red sulfur atoms were released from the thermal decomposition of cyphene, which is another component of the catalyst solution. They bound and coat on the surface, which inhibits further catalyst particle growth. Until this step, we have a typical active catalyst particle for the CNT growth. Amorphous carbon, shown in orange here, is generally considered as a major byproduct in hydrocarbon pyrolysis, and its deposition on the catalyst particle surface rendered them inactive. Water selectively reacted with the amorphous carbon, and the coating removal revived the catalyst activity and elevated the synthesis efficiency. Additionally, smaller size CNT could be achieved as a result of the catalyst size shrinkage. In this work, we included deionized water into the system solution to provide a more homogeneous and uniform distribution. Based on the amount of water added into the standard catalyst solution, 3 groups were denoted as CNT0, CNT1, and CNT2 were investigated in the later sections. Here we're showing the in-house FC-CVD setup for double watt CNT synthesis. On the left-hand side, we have an injection pump to control the catalyst feeding rate, a commercial alumina tube reactor, and on the other side, a rotating mandrel covered with Teflon sheet to serve as a sample holder. Here is a video showing the aerogel-like CNT socks being continuously collected. The stretching force from the rotating mandrel induces a mechanical stretch on the CNT to slightly align the bios, which we'll talk more in details in later sections. One of the most basic characterizations to assess the CNT quality is servogravimetric analysis, TGA. Here we're comparing the as-produced CNT from both control group and the water-containing systems. With the increasing water concentration, the first derivative weight peak showing in red were observed to shift to a lower temperature from 589 all the way to 574 Celsius, indicating the increasing amount of higher curvature, possibly smaller diameter CNTs, because of their higher reactivity with oxygen. The second derivative weight peak occurred at approximately 650 to 660 Celsius, and it referred to the oxidation of the multi-watt CNT as another component. With the addition of deionized water, this peak shifted left as well. A possible explanation for this is that the wall counts of multi-watt CNTs were significantly reduced because of the catalyst cleaning effect, increasing the oxidation reactivity. With even higher water concentration of the CNT2 groups, the 2 derivative weight peaks of similarly lower intensities occurred, which may suggest a transition to a more homogeneous CNT sizes and wall counts distribution. We have also noticed a surprisingly increasing trend of the catalyst residue from 18% all the way to 24%. To better understand this trend for CNT0 and CNT2 group, we took out samples during the TGA at 600, 700, and 800, and we examined the samples using SEM and EDS. For the as-synthesized samples, the EDS results indicate a similar catalyst residue starting point of iron content at 10.55 and 10.54%, presumably due to the identical synthesized conditions, except for the water concentration. At 600 Celsius, which is about 550 Celsius on the sample, the relative iron content of the CNT2 group increased to over 20%, suggesting the initiation of carbon oxidation, which corresponded with the first derivative weight peak in the TGA curve. And the control group remained relatively constant. This discrepancy was further magnified at 700 Celsius when the CNT2 group accomplished the oxidation. The oxidation of CNT0 group was not complete until 800 Celsius. The earlier oxidation of the water-assisted CNT2 group samples could be attributed to their smaller diameters, resulting from the removal of amorphous carbon layer on the catalyst nanoparticles before the CNT growth. Raman spectroscopy is a non-destructive chemical analysis technique based on the interaction of laser with the chemical bonds within the sample. For carbon materials, focuses are normally made on the sp2 and sp3 hybridized carbon at approximately 1585 per centimeter. The G band is characteristics of the ordered graphitic structure, and it corresponds to the carbon atom vibrations along the CNT axis. A disorder induced D band at 1310 per centimeter indicates the relative amount of the defective impurities or other symmetry breaking defects, especially amorphous carbon in our case. Therefore, we use the intensity ratio of the two band, Ig over Id, or as a direct measure of the CNT quality. Under identical conditions, the addition of water increased this ratio from 725 all the way up to 10.23. This CNT quality improvement could possibly be attributed to the effectiveness of catalyst cleaning by amorphous carbon removal. We also noted that the G band exhibited an asymmetric line shape with a weak peak appearing at 1590 or 1595 per centimeter. This is likely associated with the large amount of multi-walled CNTs due to the diameter variations among different tubes in a typical CNT assembly. This asymmetric feature became less conspicuous as the water concentration increases from top to bottom, suggesting a narrower diameter distribution of multi-watt CNTs with fewer disorders. The internal structures of the S-collected CNTs were reviewed with high-resolution TEM in this slide. For the control CNT group, the predominant component observed was multi-watt, with diameters ranging from 19 to about 23 nanometer. The addition of deionized water into the catalyst solutions transitioned this composition towards more double-watt CNTs. Double-watt CNTs started to emerge in the CNT1 samples, accompanying some multi-watt with more than 10 watts. With an even higher water concentration, the CNT2 group demonstrated a great majority of double-watt CNTs, and the diameter ranges was from 10 to 15 nanometer. These findings were in good agreement with the TGA derivative peak shift to lower temperatures that we have talked about earlier. By now, I believe that we have gained some understanding about the quality improvement of the as-collected CNT. With resin spraying and the curing process, we fabricated a CNT BMI composites with 3 different CNT samples. To evaluate the mechanical properties, tensile tests were performed, and substantial differences between the axial and transverse directions among all the groups can be explained by the stretching-induced alignment during collection. Along the alignment direction, the CNT0 and CNT1 composites demonstrate similar tensile strengths of about 535 megapascal, showing in black here. A 21 increment in tensile strength was observed for the CNT2 composites. The Young's modulus of the water-assisted group were about 27 gigapascal, and this is about 16% higher than that of the control group. The improved mechanical properties could possibly be accredited to the decreased number of CNT walls and smaller diameters. Additionally, less amorphous carbon with the water cleaning effects may have enhanced the interface. The transverse tensile stress strain curves were found to be very similar, very close to each other due to the weak intermolecular bonding. To characterize the electrical improvements, a 4-probe configuration was set. Similarly, substantial difference in the electrical conductivity along 2 directions were found, once again indicating partial CNT alignment. We see that both water-assisted groups, the CNT1 and CNT2 composites, showed higher electrical conductivities at around 1700 Siemens per centimeter, which is about 16% increase when referenced to the CNT0 composites. Here is a table summarizing the mechanical and electrical properties. Interestingly, both the mechanical and electrical properties of the CNT composites exhibited a consistent anisotropic ratio around 3, which is presumably an indicator of the stretching-induced CNT alignment. To further study the mechanical properties of nanocomposites, we conducted nano-indentation tests to review more detailed microstructure property relationships and to provide nanoscale insights of elastic modulus and indentation hardness. The S-collected CNTs were saturated in BMI solution and sandwiched in between the unidirectional carbon fiber BMI prepreg before curing. The carbon fiber prepreg was designed to provide support because this is a cross-sectional test. It is very obvious that the reduced modulus shown increased significantly, probably 2 to 3 times, compared to the tensile Young's modulus that we talked about earlier. This is probably because that the 2 methods, the 2 measurements, are very different in nature. The higher modulus from nano-indentation could be originated from the characteristics of the CNT composites, in that the tensile properties are more sensitive to the low transfer between CNT and the resin matrix, compared to the compressive properties reflected in the nano-indentation test. The modulus improvement could also be attributed by the fact that the nanoscale nano-indentation test exclude the influence of discontinuous CNT bundles. Interestingly, the anisotropic ratio from the nano-indentation test of the CNT composites was also around 3, which is very similar to what we have observed from the tensile and electrical conductivity measurements. A quick summary of what we have learned so far. We were able to achieve a continuous CNT synthesis and collections with water-assisted FC-CVD. And the addition of water helped us to selectively remove the amorphous carbon layer and reduce the amount of multi-wall CNTs in the product, yielding more double wall with reduced diameters and improved quality. The mechanical and electrical improvement could be attributed to the water cleaning effect, which led to improved nanotube quality and a better interface. A consistent anisotropic ratio around 3 was observed from various measurements as a direct measure of the mechanical stretch-induced alignment. We are very grateful for Air Force and NASA for funding our research. And personally, I would like to extend sincere appreciation to all the SAMPE personnel for devoting so much time and effort to make this happen for us, especially during this very special pandemic time, probably once in a lifetime. This is my first and very probably my last URS presentation at SAMPE, and I have really enjoyed every second of it. Thank you so much. I know that we may not be able to do a regular Q&A session in this way, but if you have any questions in any way about this talk, please feel free to email me at this address, and I'll be more than happy to help. I hope everyone stays safe, and thank you very much.